Welcome back. For this task, we're going to create a new machine learning model using the decision tree algorithm. And this is also used for classification purposes, for a classification task. The difference between the decision tree algorithm and the neural network algorithm we have used in the previous task is that the decision tree can be can give us information regarding the reason behind the classification results for certain records. For example, if one of the customers is classified as a high value, lifetime value customer, we can look at the model and we can ask for the exact conditions that the algorithm has used to identify that customer as being a high value customer. And those conditions and statements can be understood by humans, by the operator. So I'm going to refresh the data again from the table inside the database schema, which is used by the Python code to run the machine learning models. And here we have the first 5 records in our table again. And I'm going to drop the LTV numerical value column because this one is not used for classification. It's not useful for classification purposes. We're going to use this column later in one of the regression tasks, machine learning tasks. So we're going to use again the lifetime value bin classification column, which has 4 values: low, medium, high, and very high. Let's see also the shape of the data frame we just created from this table. It has 15,000 rows and 30 columns. This is the entire data set that we have, and this is the data frame we just retrieved from the database again, just to make sure we have the clean data we can use for the decision tree algorithm in this classification task. And then I'm going to do a custom split. This time we do a split 80-20, which means 80% is going to be used for training purposes, 20% of the data is going to be used for testing. And we also receive the number of rows in the 2 splits. The training is going to be for using the 12,000 rows and testing 3,000 rows. The decision tree algorithm, the same as it is similar to the neural network algorithm in the way we can train it. And exactly in the same way, we have to split the training data between 2 matrices, one with the attributes and the other one having just one single column with the labels. So we have train X with all the attributes. We are dropping the LTV bin column with the labels, and train Y with the labels. It's a matrix with just one single column. The testing data will be exactly the split, the second part of the split we did in the previous block. So we don't do anything on the testing data. And then we can also check if the database has other values than the ones we expect to have in our LTV bin column. We expect to have only 4 values, and if we have other values than those 4 values, the classification can be compromised. So we can do that by opening a cursor and querying the unique values in that column directly. And then I'm going to close the cursor just for cleaning up returning the connection to the connection pool, cleaning up the session I opened with the database for the cursor. The next step is to create cost matrix. The cost matrix specifying its mechanism of influencing the model to make certain decisions, and specify that if we make some decisions which are not good for the business, then we have some penalties and or some costs involved. For example, in the cost matrix, we have values for each one of the possibilities between the actual target value, which is the pre-label we already have, and the predicted value by the machine learning model. The sum of all the values is 1 between for each one of the possibilities. So for example, if the actual value is low and the predicted value is also low, this doesn't have any cost because this is a good prediction. This is the exact value we are looking for. But if the actual value is low and then the value is wrong, if it's medium, we have a cost of 0.3. If it's high, 0.3. And if it's very high, in this case, the result is bad for the business. And in this case, we have a higher cost. In the same way, we have bigger costs. For example, if the actual value is high and the predicted value is low, or the actual value is very high and the predicted value is very low, because in this case, we can lose a customer. And that's why we specified higher values for the penalty to be applied to the machine learning model in case of this wrong prediction. And the model will try to avoid these penalties. So this is how the cost matrix works. So let's create the cost matrix object. And this object will be used in the definition of the later in the definition of the machine learning model. And then if you want to learn more about cost matrix table, you can click on the link here and you can go to the documentation, read more about it, how it works. And next step is to specify the data model, the machine learning model settings. We're going to change just one single parameter in this case for the demonstration purposes, and this is also used because this is for training purposes, and we are not trying to make exact predictions. We are not using this one in production now. So I just want to simplify a little bit the lab, and I'm going to specify one single attribute in the settings for the algorithm. If you want to see all the possibilities, all the settings you have available for this decision tree algorithm, you can click here on the link and it will take you to the documentation. And then I'm going to use the settings to create an object, a data decision tree machine learning model object. And then I'm going to train the model using the training data from the two matrices, one with the attributes and the other one with the labels. And then I'm going to also use the cost matrix in the training of the model, just to make sure we avoid those wrong results I was explaining earlier in the cost matrix definition. It takes maybe a few seconds to train. And here we have the details about the model. You can see here. So let me go up. So you can see the algorithm name, mining function classification. You can see all the settings. We have modified just the max depth of the tree. This is the number of levels we have between the root node and the leaves nodes in the decision tree. It's a long story how to explain it, but we advise you to go to the documentation and check it to see more details. And then I'm going to use the model to make some predictions. We're using the testing data. We use the second split here, the 20% of the data we saved for testing purposes. And also when I perform the test, I drop the results column, the classifications column, the LTV bin classes, because I'm not going to give the algorithm and the machine learning model the result I'm expecting the model to give me. But when I print the results, I'm going to include some columns about customers to be able to identify customers, and also the pre-label LTV bin column, just to compare the results with the predictions, with the actual values. So here we have 10. It is truncated. The output is truncated, and we have 10 records in the output, just to have an idea about the results we received from this data, from this machine learning model. So we have one good prediction here, another prediction which was perfectly fine. We have a wrong prediction here. The actual value is high, predicted value is medium, and then the rest of the predictions we have here, they look good. So this is just a sample of the outcome. We can check all the data if we want, but in this case, we are going to go ahead and investigate what has been going good and bad in the machine learning model. So let's retrieve the confusion matrix. The confusion matrix is a technique, a summary of the true positives, true negatives, and false positives, false negatives, to identify what has been predicted well and what has been predicted wrong using the machine learning model we just created. In this case, we have 4 possibilities for the predictions, and we have 5 columns in the confusion matrix. The actual value of the pre-labels we already have for the customer records, and then the predictions. So for example, from the customers which are low customers in the pre-labeled data we have, 244 have been predicted correctly as low. 6 has been predicted as high, 15 as medium, and 1 as very high. So these are the wrong predictions, high, medium, and very high. From the very high customers, 209 have been predicted correctly, and 86 have been predicted wrong as high customers. But none of the very high customers have been predicted by low or medium. This result may have been influenced by the cost metrics we have used when we trained the model, just to avoid very high customers to be predicted as low or medium, in order to lose those customers when we decide to which customers we can go ahead and make an offer. So you can see here from the confusion metrics, we already have an idea that the cost metrics table has been working and has been helping us to improve the way the machine learning model is predicting our customers. So let's see the customers with wrong predictions and get an idea about what predictions have been made wrongly in our results here. And we can also return the probability for the wrong predictions. For example, we have a column which is the probability of the prediction. So how sure is the machine learning model that the prediction is exactly the value we are looking for. For example, for these predictions, which are correct, the system, the machine learning model is sure about 80%, 78% that the prediction is good. But in this case, for example, which is a wrong prediction, the actual value is high and the predicted value is medium, the system, the algorithm is 95% sure that the prediction is good. So you can see here that the probability column can give us an idea about what the machine learning model thinks about the results that have been predicted and returned to us. And then we can also see the wrong predictions only. Here we have all the predictions, and we can also see the wrong predictions only with the probability of the prediction to identify, and we can also order them in by the probability percentage. So you can see here, for example, a customer which actually it has an actual value of high and has been predicted as medium. The system is 100% sure that the prediction is good, and we can tune it to make it work better in this case, because it is not very well. And let's see the scoring for this prediction model, for this ML model we just executed. So the scoring for this model is 91%. 91% of the predictions are correct, and this is the accuracy the machine learning model has achieved in this example here. We can try to improve the accuracy and the scoring by, for example, tuning the model and changing some of the attributes we have defined in the settings when we created the model. In this case, I'm going to increase the max depth of the model from 8 to 9. So I'm going to increase this one, and I'm also going to train the model. You will see that the training will take longer because an increased max depth of the trees in a decision tree will increase the complexity of the model exponentially, and the time it takes to train this model is going to be a lot longer than the one we have experienced in the previous model, in the previous definition of the decision tree we just executed. And then we have to decide if it makes sense to use so many resources to increase the accuracy of the model and how much accuracy we have achieved for this new model. We always have to look for the balance between the time it takes to train a model and to execute it, and also the resources this model is consuming, and the accuracy of the model. For example, if we achieve a very low difference in accuracy and it takes maybe 10 times longer to train and to 10 times more resources to execute this model on our database, I don't know if it makes sense, if it makes sense to use this complex model in our machine learning task. So here I'm going to pause the recording, and I'm going to come back because it takes about 10 minutes to train. So now the model has been created, and it has 9 the tree max depth is 9 now, and you can see that it took a longer time to create. And this is the question we have. Let's see how much we have improved the accuracy when we score the model. So I'm going to check it, and we have improved the accuracy just 1% improvement. And we have to decide, okay, does it make sense to have such a complex decision tree model and so many resources consumed to train this model, and improving the score from 91% to 92? Well, it depends. And if we have a very good model and we are really happy with the model results, we can export it to a table. This is the function we use to export the model to a table in a serialized model. It is actually written in binary format. So let me do it. And I think the table already exists because I did a test before. That's why I'm getting the error. Now I just specified another name for the table in my schema, and it worked. And then I'm going to see the type of the machine learning model, and it's binary. As you can see here, it's on OML4Py type. And we can check the first 100 characters of this binary blob we written that table. This table can be exported and can be imported, for example, in another database. You can take it from this on-premise location to another database you have on-premise to use the machine learning model, or you can use it in autonomous database in the cloud to run OML notebooks using this exported model from this database here. So you can share machine learning models between databases. So I'm going to run this pull request for the first 100 characters of the binary model, and this is the output here. And this is it. Thank you very much.